Hello everyone, this is Sunny Kumar from IIT BHU and welcome to my channel Code with Sunny, and today I am going to discuss the problem Russian doll envelopes. Index number is 354 and the problem is of hard type of Leetcode. Okay, so let's discuss the problem now. We have been given a 2D array of integers named as envelopes, where it consists of two keys wi and hi for every index I of the envelope vector. Okay, which represents the width and the height of an envelope. Okay, one envelope can fit into another if and only if both width and height of one envelope is going to be greater than the width and height of the other envelope. Okay, and we have to return maximum number of envelopes can we build, that is we can put one inside the other. And there is one note given in this problem: we cannot rotate an envelope, that is width of I and h of I cannot be swapped for a particular envelope. Okay, and here are two examples given, we are going to discuss that also. Okay, so let's look over the constraints now. Envelopes length, that is the length of the total number of envelopes, or you can say the count of the total number of envelopes, can go at most 5000, 5 into 10 power 3. And the envelopes of I, that is there will be only two parameters for every envelope, that is width and height, and wi and hi can vary at most 10 power 4. Okay, so how we are going to do this problem and what would be our approach and prerequisite to solve this problem. So let's understand this with the help of example, and let's generalize this how we can solve this problem in the best efficient way. Okay, so let's move further with the help of example. Okay, so here I have taken an example array. There are four envelopes. You can see the first key is going to denote the width, and the second key is going to denote the height. Okay, so first let's understand this statement. One envelope can fit into another if and only if width and height of the one envelope is greater than the width and height of the other envelope. Okay, so basically for a given envelope we have been given two parameters, the width and height. Let's say w1 and h1 for one envelope. Let's say call it as e1. Okay, and we have been given another envelope, let's say w2 and h2, you can see are the width and height for that envelope, and let's call it as e2. Okay, now the question says if w1 is going to be strictly less than w2, and you can let me write, and h1 is going to be less than h2, then we can easily say e1 can be put inside the envelope e2. And if this is possible, we can easily claim that the maximum number of sequence of envelope that can be possible as our answer, that is one can be put inside another, is 2. You can see easily see two envelopes can be put like that, e1 can be put inside e2, so the count of envelopes is 2 simply. Okay, so if we are given only two envelopes and these two envelopes satisfy the conditions around each other, then we can say our answer for this case will be 2. Okay, so this is the basic example of this question. We can how we can generalize this for n envelopes. This is the main point of this question. Okay, so let's understand that also. Okay, so let me erase this stuff now. Okay, so now the questions, we can understand this question with the help of some modifications to the some classical questions. And what is that classical question? Okay, so let's begin with the simplest example. Suppose we have been given 5 elements, or you can say 6 elements of the array like that. Okay, so what should be the, if we have been given this 5 elements and we have been asked that these represent the sizes of the envelopes, and let's say the parameter in the previous case we have been given two keys like w1 and h1, and let's say we have been given this array, that is array containing one elements, and we have to find out what should be the maximum length of the sequence of envelopes we have to find out, so that one can be put inside the other, and the condition is, that is we have to depend only on the single element. Here you can see we have to depend on the two keys for a particular envelope, and let's say we have to depend only on the single key. And what we have to do in this case, you can easily see one envelope can be put inside the other. Let's say if and only if k1 is less than k2, where k1 and k2 are the parameters of two envelopes. Okay, so let's find it out. We can easily say for every envelope our answer should be minimum 1, that is we can easily say. Now what should be the length of the longest envelope, the sequence of envelopes like e1 should be less than e2. and should be less than E3, and so on. Okay, if this is possible. Okay, so let's find it out. You can see in this case also 3 is less than 4 and 4 is less than 5. So our answer would be like, let's say if I number this envelopes like E1, E2 and so on up to E5, we can easily say E3 and E3 is less than E4 and E4 is less than E5 are the sequence of envelopes whose size is total is equal to 3, and this is our answer. And what about there are more sequence of envelopes you can see, and you can also find this like 5 and 6 where E1 is less than E2. E1 can be put inside E2. This is our answer, but this includes only two envelopes. This is not the maximum answer for this problem. And you can see 3 is less than 4 and 4 is less than 5, which can be our answer. That is, even E3 can be put inside E4 and E4 can be put inside E5. So our answer for the length of the maximum sequence of envelopes is 3. Okay, so how can we this if see if a single parameter is given for a particular envelope, this can be easily find, and you can generalize this case like for this array. If you are aware of the dynamic programming concepts, you can easily see if n square is going to be around 10 power 7 less than equal to 10 power 7, this problem is nothing but a classical problem of LIS, longest increasing subsequence. You can also say longest is strictly increasing subsequence. Okay, so we have to find the longest strictly increasing subsequence of the particular array. If a single key is present, this can be easily done. This is a classical problem of longest increasing subsequence, strictly increasing subsequence. Okay, but what is given in this problem? Okay, this problem defines that we for every particular envelope we have two keys, width and height. So how we are going to do that? So the it is simple that if this problem is the modification, you can say, or you can say the application of the classical problem, this must be this problem can be easily done with that also by doing some cool tricks. So what is that cool trick? So let's understand this now. Okay, so let me erase this stuff now. Okay, so here I've taken the examples as you can see. Now let's find out the dynamic programming solution of this, that is the modification of the longest increasing strictly increasing subsequence of this array. Okay, so the condition is, you can see, h1 should be less than strictly less than h2, and and w1 should be strictly less than w2. Then we can say e1 can be put inside e2. Okay, so how we are going to do that? So first thing is that the optimal way is, let's why not sort this key 1 and key 2 on the basis of one of the keys. So we are aware that we have two parameters, w1 and h1. Okay, so why not sort with this first key, so that at the beginning of the envelope array we have the first key as the minimum. Okay, so this is the optimal one, because if we have the minimum key, then we can start think easily that how we are going to form the longest increasing subsequence with the help of the two keys. Okay, so let's do that. So if you are going to sort that with the help of the first key, then you can see we have the parameters like 2 comma 3 will be the first one, and the second one will be 5 comma 4 simply. And what about the third one and the fourth one? It is simply 6 comma 4, and it is simply 6 comma 7. Okay, so these are the keys. Okay, so what should be the minimum answer possible with this modified array containing the each parameter, each key, each index has two keys. Okay, w1 and h1. So what is the minimum answer possible? That is, minimum answer possible is always 1, because we can always have a 1 in envelope. Okay, and what should be the maximum answer possible? Maximum answer possible is nothing but longest increasing subsequence of this array. Why I am focusing on the longest increasing subsequence? Because we need to have to satisfy this condition, and we need to choose a sequence of envelopes. That's why I'm focusing on longest increasing subsequence. And longest increasing subsequence, because h1 the e1 should be put inside e2 and e2 should be put inside e3. So, okay, so let's find out the longest increasing subsequence with the help of the dynamic programming. So let's define a dp array where dp of I is going to denote that what is the longest increasing subsequence of envelopes that we can have possible up to this index. Okay, you can easily see up to this index we have only one envelope, so our answer should be 1. And what is the longest increasing subsequence up to possible up to this envelope? You can see 2 is less than 5 and 3 is less than 4. Note that I am talking about strictly less than. So what is the longest increasing subsequence possible up to index number 2? That is it is E1 and it is E2. E1 can be put in easily inside E2. So our answer should be like 2 up to this index, that is E1 should be put inside E2. Okay, and what is the longest increasing subsequence possible up to this index, that is the third index E3. Okay, so let us find it out. So can we put E1 inside E3? Yes, we can easily put. So our answer is 2 now. And let's check, can we put E2 inside E3? No, we cannot put, because 5 is strictly less than 6, but 4 is not strictly less than 4. So our answer would become 2. And what are the sequence of operations, sequence of envelopes possible? You can easily see the sequence of envelopes possible is nothing but E1 should be put inside E3. If if I am going to deal with that, okay, that is the maximum number of sequence of envelopes possible up to index 3, and it is, you can see, we can write it as E1 should be put inside E3 up to this one. Okay, so this is done. So I am going to find out what is the maximum number of sequence of envelopes possible, that is I am going to put one envelope inside another. So it is E4 now. So let's find it out. E1 can be put inside E4, yes, and E2 can be put inside E4, yes, because you can see 5 is strictly less than 6 and 4 is strictly less than 7. Can we put E3 inside E4? No, we cannot put. So what is the length of the longest increasing subsequence possible? That is, you can see 2 plus this one, that is 3. That is, we can, in this case, that is, we can put E1 inside E2 and E2 inside E3, sorry, E4. So answer would be 3 envelopes. Okay, so this was the basic, you can say, dry run, and how we can generalize this case. Okay, so so having the solution of dynamic programming, let's iterate for I starting from 1 to n strictly less than n, that is I from 1 to n minus 1, and for every index I iterate j from 0 to j less than I, and find out what is the maximum sequence of envelopes possible for the ith index. Okay, so if what is the maximum sequence of envelopes possible for the ith index if I consider the last taken envelope as jth index. So if you're not going to understand this, no need to worry about, let us write a DP relation for that here. Okay, okay, let me erase this one. So let me write a DP relation, that is for every I starting from 0 to n minus 1, and I am going to find, and let's start from j equal to 0 to j less than I, and find out what is the maximum sequence of envelopes possible for this ith one. So if dp of I is going to be what, maximum of this dp of I, already taken values of dp of I, and 1 plus dp of j. And why I am going to do this 1 plus dp of j? Note that this is going to be done only when, if let's say I am at envelope E3 and I am doing for envelope E5, and if E3 is going to satisfy for E5, then I am going to do this condition. Okay, this is basically the classical longest increasing subsequence of dynamic programming solution. Okay, just a modification if we are using the two keys. Okay, so let's look for the code now. Okay. Okay, so this is, here you can see O of n square dynamic programming. I am also going to discuss the O of Nlogn solution also after this one. Okay, so you can have a maximum envelopes also. Sort the envelopes first, envelopes vector. Sort first to get the minimum width at the beginning. As I have already said, this is the optimal. First place some key at the beginning. Let's say first key. Why not width? Okay, so fill dp of I equal to 1. That is the minimum answer. Always includes some envelope. Okay, I start from 1 to n and take the parameters h1 and w1, envelope psi of 0 and envelope psi of 1. Okay, I have taken this one wrong, and if it is a variable, no need to worry about. Okay, h1 and w1. Okay, now I am iterating from j equal to 0 and j less than I, and for every j I need to have a h2 and w2, height and width. Okay, and find the longest increasing subsequence up to the current index satisfying this given condition. That is, if my current h1 is greater than h2, you can see, and W1 is going to be greater than W2, it means that this jth envelope can be put inside the ith envelope. So what is the maximum length of the increasing subsequence possible for this ith index? That is max of dp of I and 1 plus dp of j, because we need to add 1 because I am going to include my current envelope also. So I am going to do this for every I. And finally, what should be our answer? Answer would be simply the maximum element of the dp array. Okay, so let's submit this code now. I think I have not submitted yet if any of the solution of this one. Okay, yes, it is good. Okay, so let me have some another Nlogn solution also. I have already written over here and still I haven't checked. Okay, oh, let me uncomment this code. Okay, this is Nlogn dp also. So the basic idea of this one is to reduce the O of n square solution to of dp to O of Nlogn solution. Before understanding this one, you can also think about longest increasing subsequence for a particular array. Here we have two keys. You can also think of a single key also, and we can have also have an Nlogn solution for that also. So how we are going to modify that Nlogn solution for a single array with a single key to here the double key, that is every index contains two keys. How we are going to do that? So let's understand that also. Okay, so the first thing is we need to sort the array first. Okay, so in this case, if I'm going to sort the array first, there are there are two problems that arises. Okay, so we need to sort the array with the help of the comparator. So why we are going to sort the array on the help of the comparator? Okay, so first thing is let's understand this with the help of the example also. Okay, okay, so again I need to erase this stuff also. Okay, so okay, so I need to erase this one also. Okay, so let's understand that also. First thing is we need to sort the array first. Why we need to sort the array first? We need to sort the array first to work upon only one key. Okay, so let's sort the array first. It would be like 2 comma 3, and you can also see we have a 5 comma 4, and then we can say 6 comma 4, and then we have a 6 comma 7. Now it is sure that if we work upon this first key, or you can easily observe that this 2 is going to be this 5 and this 6 and this 6 always are in non-decreasing order. Okay, so this is valid. So how we need to now work upon the second key? So how we need to work upon the second key very cleverly? How we are going to do that? Okay, so one thing that should be noticed, that let's say we have two keys like okay, 2 comma 3, and let's say we have another key like 3 comma 3. Okay, so you can easily think that first key, that is you can say 2 and this 3 always satisfy this condition, h1 is less than h2. Can this envelope e1 should be put inside e2? No, we cannot say, because you can see this 3 is always going to be this one. This is exactly equal to the one, that is 3 is going to be 3. So e1 cannot be put inside e2. So how we are going to do that? Okay, so let's have a better solution over that also. Okay, so this was the good example, and let's take another example like okay, like we have a 2 comma 3, and we have like okay, so we let's say we have a like again 2 comma 3. So can this be possible? No, we cannot say this is possible, because this is a non-decreasing one, and this is also in also what, non-decreasing one. So this is not possible. So the h1 should be less than h2, that is strictly less than h2, and w1 should be strictly less than w2. Okay, so this says that if I need to have sort the, let's say we have two keys for a particular envelope k1 and k2. So I need to sort this k1 in strictly increasing order, or let's say sort in non-decreasing order. But for if two keys have let's say k1 and k2, okay, let's say we have a k1 k11 and k, let's say k12, and if k11 is going to be exactly equal to this k12, I need to have to sort this k21 and k22 in decreasing order, so that we cannot have a invalid answer. Okay, if after if I am going to perform the longest increasing subsequence of Nlogn operations. Okay, this is the main logic of this question of Nlogn solution. We need to sort the first key in ascending order, and we need to sort the second key if my first keys are going to same for the two envelopes, and we need to sort for the second key in what, in going to be decreasing order. Okay, so let's do that also with the help of the comparator. Okay, this one and this one. So basically, if two keys I have taken with the help of comparator, if A0 is less than B0, just return true, and if both is going to be same, just return the, if A1 is going to be greater than B1, it says that I am going to return the second key on the basis of decreasing order. Okay, and finally return false. If you're not going to aware of this one, no need to worry about. I have mentioned that in my description section of the video. If you are going to check that also for the understanding of this comparator, how we are going to use this in our program. Okay, so here we have taken the an envelope size, and here I have taken a store vector. Okay, that is basically nothing but pushing the longest increasing subsequence possible up to, or we can say, if you have iterated for the first I elements, what is the longest increasing subsequence possible for this up to ith index. Okay, this is going to store basically the elements of the array. Okay, so let's start with the base one, that is push the first key. What is the first key? You can easily see this. I am going to if width are already sorted in ascending order, I need to work upon the height one, that is the second parameter for every index. That's why I put the envelopes of 0 and 1, and the answer is now 1. And for every I starting from 1 to n, just take the lower bound of this in my increasing subsequence of the second key of the heads. Okay, and if this is going to be like, I have taken the iterator, and if this iterator is going to point at the end of the my longest increasing subsequence, it basically means that this is going to contribute in the longest increasing subsequence, and we need to push the element in my longest increasing subsequence. Okay, so I am going to push that element and increase my answer by 1. Otherwise, if this is going to lie somewhere in the between of the longest increasing subsequence, then why not to replace that element with my new element? That is going to be minimum also for that particular longest increasing subsequence. So just put that star itr equals envelopes of phi of 1. Note that I am going to work on the height one, because width parameter is already sorted in increasing order. Okay, so finally return the length, and this is nothing but O of Nlogn solution, because I am going to iterate from I to 1, and I have a lower bound function also of the binary search inbuilt C++ function that is going to take log of n time. So basically I have an Nlogn solution. So let's submit this code now. I think this should work fine. Yes, runtime 40, faster than 87.8. So if you have any doubts, do not forget to mention in the comment section of the video, and I will ask the viewers to like this video, share this video, and do subscribe to our YouTube channel for latest updates. Thank you for watching this video.